So early sailing ships were these big, huge, what they call windjammers or square-rigged ships. The sails went across the ship. The wind just came from the stern and just pushed the ship along. It's like going out on the interstate and getting behind a semi-truck, you know? They were the semi-trucks of their day. They were big, slow, bulky, but man, you could fill them up with a lot of stuff. And off they went across the ocean because they just got into, well, trade winds to go out and trade with the colonies. So they'd go westward, and then if they wanted to come back home, they'd just go northward or southward, get into the westerlies, and get pushed back home. But they weren't very handy pointing into the wind or getting close to a shore. They were just kind of the big guys, bulky, out there, just getting pushed along by the main wind band. So they'd get into harbor, they'd offload their supplies, and they'd transfer into these little schooners. And notice the schooner has a set of sails that goes fore and aft. It's lined up along the keel or the middle of the ship. This way, this was designed more to sail north-south rather than east-west. It caught the wind from the side rather than from the stern. So this is like the delivery truck we have in the towns now. The big semis stop at the freight terminal, the little trucks pick it up, and off it goes to be delivered at your house. So ship design basically came out of the weather patterns and atmospheric and ocean circulation patterns to take advantage of what was there. Now remember, we talked about this gyre, this circulation pattern in the ocean, and notice how this circulation pattern now kind of goes hand in hand with these wind patterns. Here, the north equatorial current, that leg of the Atlantic gyre, goes from east to west, and notice how the trade winds are blowing across that, pushing it along. Then, as I look at the North Atlantic current coming back from the west part of the basin to the east part of the basin, Coriolis effect is swinging it out there, bending it around, but then it gets into the Ferrel cell westerlies, and they help push it back. So the pattern isn't just Coriolis effect, but the pattern now combines the oceanographic circulation pattern of the water with the atmospheric circulation pattern. And they work hand in hand. Okay, so true or false? I want you to think back to what we were talking about with Coriolis. When a cannonball is fired northward from the equator, so I'm dealing in the northern hemisphere, which way will it veer? And I'm saying it'll veer toward the east or clockwise as it heads north. I'll give you all 25 seconds so you can think this one through.
It's fired north. It's going north.
I thought it was east. It's east.
Okay, everybody in?
Hold on.
Yep.
Good to
Better
go.
vote. Yep, okay. 68, we got them. All right. Let's see how we did. Yeah, exactly. 'Cause as in the northern hemisphere, it's going to go clockwise, isn't it? If it's going north, it's going to veer off eastward. If it's coming from the pole toward the equator, it's going to veer westward. But either way, it's still all clockwise. Okay? All I've done is turn around 180 degrees, so I'm just getting an east or a west viewpoint, but it all adds up to being clockwise rotation. Okay. Okay, so let's talk about hurricanes. Storms are the thing that always catch our attention, especially if we live in the Gulf Coast. And what we're looking at with this atmospheric circulation, with what we call hurricane, is it's a cyclone. It's just a big, giant regional atmospheric disturbance. It's regional. It's high winds, usually with precipitation, rain. But notice the thing that it always has is high winds. Okay, we kind of focus on the rain part usually, but it's the winds that are the thing. And it is simply a huge rotating mass of low pressure air. And the winds are converging and ascending. Now, in the North Atlantic, in this part of the United States, we call this a hurricane. In the Western Pacific, they call it a typhoon. In India, they call it a tropical cyclone. In Asia and the Pacific, they call it a monsoon. It's all the same thing. It's a big, rotating, uplifting mass of low-pressure air. Okay? So it just goes by a bunch of different names. But we have two versions of it. One is a tropical cyclone, and as you might guess, that's made in the tropics. And what's the cell that's typical of the tropics? What's its other name? Hadley cell, yeah. So these are Hadley cell cyclones. The other are what we call extratropical cyclones, and that doesn't mean it's got extratropic in it. It means anywhere outside of the tropics. And these usually generate at the juncture, the point where the Ferrel cell meets the easterly polar cell at the 60th parallel. So that's north of here. We're at not quite the 45th parallel. If you want the 45th parallel, it's halfway from the equator to the pole. That runs right through the Leelanau Peninsula, right by Traverse City, Gaylord. That's the part of Michigan where the 45th parallel cuts through. We're at about the 42nd or so down here. So, two different places that these cyclones evolve, and slightly different generational kinds of mechanisms. Where the polar easterly cell and the Ferrel cell kind of slide past each other. Remember, we've got the westerlies in the Ferrel cell, the easterlies in the polar cell, so we've got winds blowing in opposite directions in these cells. And at the 60th parallel, where they're blowing past each other, that's what's known as the jet stream. And the jet stream moves north and south. It just doesn't stay as in a straight single line at the 60th parallel. But it wobbles and moves up and down. The way they found out about the jet stream was during the Second World War. They didn't know about it. And for the first time, as we started to bomb Japan, the B-29 Superfort bombers came off the line. And they were the first bomber that we had that had a pressurized cabin. All the rest were just open. So it could fly higher than any of the other bombers could fly. Instead of being limited to about 17,000 feet, it could get up to about almost, not quite 30,000 feet. And they used that to advantage. But it also put them into new territory. And as they started to capture the islands through the Pacific and use those as bases then to go over and bomb Japan, they were finding that their calculated speeds and runs back and forth to Japan weren't working out quite like they thought. They were getting over there an hour early and taking an extra hour getting home. They were running into upper level winds that they had never thought about. It turned out they just discovered the jet stream. And this jet stream now is essentially the polar easterly sliding past the westerlies of the Ferrel cell. So here we are. Here's the polar cell, here's the Ferrel cell, here's the jet stream. I've got cold air flowing from east to west in the polar cell, warmer air in the Ferrel cell moving from west to east, the westerlies, And everything's fine as long as it's a nice, fairly even straight front and things just keep sliding past each other. But what happens when the front starts to get a bump in it? All of a sudden, it doesn't make for a nice smooth transition of winds past each other. Instead, it starts to set up a low pressure area. And things start to curve into that bump. So, here we go, cyclone, right? I've got a rotating mass of air, it's a low pressure area. That means it's going to be lifting up, isn't it? It's going to be ascending. Low pressure means less dense, it's going to be lifting. And here we go. All of a sudden now, that front's going to start to bend over again, kind of coming in on itself. It's going to go into an occluded front, and we're just going to see the beginnings of the cyclone. This is an extratropical cyclone. What we see is these guys tend to form during the fall time period, sometimes spring, but fall is very typical for this to occur. Here's an extratropical cyclone. You can see the coast of the United States. Here's California, Oregon, Washington. Here's the inside passage up through British Columbia, Alaska, the Aleutian Islands. This thing's taking up the entire northern Pacific Ocean. It's huge. And look at it. Here it is, just spinning in on itself. And notice the banding. You've got this really tight nebula or a nimbus cloud, and then you've got kind of this scuddy stuff in between. This is pretty typical of one of these extratropical cyclones. It kind of gets this banding pattern to it. Now, something ought to be catching your attention here. What's wrong with this picture? I'm in the northern hemisphere, right? Which way does Coriolis turn in the northern hemisphere?
Clockwise.
Clockwise. Which way is this thing spiraling up?
Counter.
Counterclockwise. So is that telling me that Coriolis doesn't always work?
Yeah.
Yes.
Somebody superimposed it. Well,
Natural laws of physics, and yet they only work part of the time? I don't think so.
Photoshop.
It's been photoshopped, that's it. Yeah. Well, let's come back to this. Is that what's happening? This is what the damage is from one of this. This was what's called a nor'easter, because in the Atlantic, they come in from the northeast across land, and this was the damage done in 1962 on Fire Island. This is one of the barrier islands right along New Island, or along Long Island. It's a real popular beach community place, very expensive. It's all, New York City's money driving it. And look at it, just wiped out. There isn't a cottage left standing. So these can be pretty devastating storms. So, okay, let's keep thinking now. What was wrong with that picture? Why? Well, let's take a look at tropical cyclones. Maybe there's an answer there. Now we're looking at cyclones that are going to form in the tropics. So instead of forming up here along the jet stream, now we're looking at things that are forming down here within the Hadley zone, the Hadley cell, within the tropics. And when you look at the zone, you just see it right along the equator, north and south, and you can see the generation areas here in orange. You see the general preferred tracks of these various cyclone swarms. And what they start doing is they form over warm water. And as that warm water starts lifting into the atmosphere, it creates a low, moist air is less dense than dry air. We figured that out, right? So all of a sudden, I've got more moist air. It's starting to lift. Air is starting to be pulled into that lift, and I start the rotation. So the thing that feeds these guys is nice, warm, moist air. That's its fuel. So obviously, along the equator is going to be the warmest, and out over the ocean is where the water's going to come from. So look at here in the Pacific. Look at how the cyclone path has all of this distance to build, develop huge, huge monsoons, huge cyclones. If you look at the cyclones that come in to Australia, that come up through India and Southeast Asia, they're almost always massive storms that far outweigh the ones that we get hit with. Look at the Atlantic. We have a fair amount of area, but it's nothing compared to the area in the Pacific. So we don't get the storms to the degree that they do over there. Okay, you can see the tracks. I can see this on one of these cool satellite pictures. Here's a picture that, was put together in about a 3-day period. So it's a pretty good snapshot of what's going on. And if you look at it, here all the warm, moist airs, you can see the Pacific region, the region here by Australia. You can see the area in the Indian Ocean. And look at this little bit right through the Atlantic in comparison. So you can just see where these storms are going to generate over this moist, warm area. So this is what one of them looks like inside. You've got this uplifting, rotating mass. And look, it's rotating clockwise. And here, it rotates off. Okay. And you'll notice it's kind of a series of walls. It's not just one single mass, but it kind of breaks into walls. And notice here in the middle, it's got an eye. Nothing much is happening there. It's all rotating around that area. The lift is up to the wall cloud area. And in the center, we've got vertical motion in the air. It's not rotating in. What's happening here in the sides is here along the surface, this air is being pulled in, and then in the eye, up it goes. So here's where we feel the storm, is where we're getting all this lateral motion in the wind. Here at the eye, it's just rising, and we don't really feel much there, do we? It's really when it comes in at the side that we feel. So, what was wrong with that picture? Well, if we look at it, that picture was rotating the correct way for the Northern Hemisphere. Big cyclones in the Northern Hemisphere rotate just the opposite of the way the Coriolis works. Coriolis should be going clockwise. Hurricanes are going to rotate counterclockwise because the air motion starts in the high pressure cell. The air starts moving from the high pressure area toward the low pressure area. Okay, the low pressure area is where it's lifting. That's the hurricane, isn't it? But as the air starts to move out of the high pressure zone, that's where it starts being affected immediately by Coriolis. So as soon as it starts moving out of the high pressure, it starts moving off, swinging off clockwise. So out of the high pressure area, Coriolis is doing exactly what it's supposed to. The initial air motion is clockwise. That means as it feeds into the low pressure area from all sides, because the low is surrounded by higher, right? So it's being fed in from all sides. Coriolis has already made its mark, and as that air swings in, it kicks off the low pressure in just the opposite direction. It's that gear effect, isn't it? Same thing going on here. So Coriolis is doing its job just fine. But what you're seeing is the low pressure, kind of the secondary. Question?
Yeah, so what happens like when a hurricane develops in the tropics in the Hadley cell, then moves up to the Ferrel cell? Does it switch its direction then? Or does it just kind of
No, it's still in the Northern Hemisphere. Okay? It's not a cell by cell deal, it's a Northern Hemisphere versus Southern Hemisphere. Okay? The question that you really probably meant to ask is what happens when it crosses the equator?
That's a good question.
Yeah.
Millions of years.
Millions of years.
Millions of years.